In this video, we're going to review rational exponents. This is a concept you learned back in Algebra 1. I'm not going to lie, it was probably one of the more disgusting concepts because you have fractions for exponents. This video is kind of already understanding that you have seen this before, so we're just going to review the basic concepts and kind of go through some simplifying to see how you would get your answers. So first thing that I want to mention, since this very closely relates to radicals, on radicals, you have a radical that looks like this. This is actually your radical. And underneath that radical, you usually have a variable or number or a combination of variables and numbers. This is called an expression technically, but underneath the radical, it's called your radicand. And technically in front of that x, we could have a 3, we could have a -2, we could have whatever number we want in front of that variable. And technically we could have variables behind it as well, so in case we wanted to have more. The last thing is whatever number sits on top of your radical. In this case, by not having a number there, it's safe to assume that that number is 2. That number is called an index. All of these pieces I'm going to frequently refer to, and especially when we go over simplifying radicals, if we haven't already, we're going to need to know these different pieces. So radical is the actual shape itself. Radicand is whatever information is underneath that radical, and the index is the number that sits right outside, so it's usually an invisible 2. In the definition for rational exponents, whenever you're given a fraction, so this means the same as b p over q, we can pretty much rewrite it in two ways. Whatever your denominator is, so both of these q's are your denominator, we always make that your index. The radical itself is going to be created because you have a fraction or a rational exponent. And then the last piece is wherever your radicand is, you'll put it underneath the radical and raise it to whatever the numerator's exponent is, so whatever the exponent in your numerator is supposed to be. This is the general form that you'll see it as. So just to rewrite it so you guys can see it, we would rewrite this with the radical since we have a rational exponent. We would put the radicand underneath, which is technically like your base b. The index will come from your denominator. The exponent will come from the numerator. Another way that you can write the exact same thing is rewriting it with parentheses. All we're doing is we're pretty much saying by definition, you can either have the exponent for your radicand underneath your radical with the radicand, or you can rewrite it outside of the parentheses. So q, b to the p power, or not p, raised to, or let's try this again. Q with the radical, b is your base, and then outside of this parentheses is p. There's really only two ways that you guys would really need to use this. And I do this, I'm going to do this later on in the rest of the video. Whenever you're given a b value under here, you can technically raise it to whatever that p power is. That will work if you had like b squared. You can rewrite it as b times b. If this p-value was like 10, it might be easier for you to simplify this expression first, following the rules of, or the order of operations. So you would do with the parentheses first, and then after you find this answer, raise it to the p power. So there's two ways that we're going to be able to solve it, and I'll show you both ways as we go through the rest of these questions. The last piece is, for these examples, I've just kind of rewritten them for you to actually show you what it would look like. So whenever you have the square root of x, it's your responsibility to understand the index on this radical is a 2, and the exponent underneath this radical is a 1. So attached to that radicand is a positive 1. Also, if you had the cube root of x, okay, well 3 is going to be your denominator, as you can see, but the exponent on x is a 1. If you're missing an exponent on a variable or number, put a 1. If you're missing an index on your radical, don't put 3, put 2. 2 is the default index in case you don't see it. And then for the last one, if you had the cube root of 2 raised to the 5th power, this can also be rewritten as the cube root of 2 to the 5th power. Especially when you're solving questions like this, it would probably be easier for you to solve or simplify this question first compared to this one up here. But again, I'm getting a little ahead of myself. So this also would rewrite the same way. 2 is your radicand, which is like your base. You would raise it to the 5 over 3 power. The 3 is your index. That's always your denominator. The 5 is your exponent on your radicand. That is always the numerator. Okay, well, now that we've refreshed your memory on just the basic definition, let's use that definition to answer these 3 questions. The good news is these 3 questions are going to give you an actual numerical value. So the first thing we're going to look at is example 1. So we have 16 raised to the 3/2 power. Okay, well, if you think back to what we just did at the top, I can rewrite this rational exponent of 3/2. I can rewrite it as a radical. The 16 is your base. That's your radicand. It's going to go underneath. The 2 is your index. That's going to go right outside of your radical. And the 3 can go inside. This is what we're solving. So technically what this problem is asking me to do is take the square root of 16 to the 3rd power. Okay, this is where you have to use your brain a bit. If I was to do 16 to the 3rd power first underneath this radical, which is technically how it's ordered, I would have to multiply 16 times 16 times 16. 2 issues. 1, you don't have a calculator, and 2, I'm not about to multiply 16 3 times. Okay, well, when you're stuck with a problem like that, is there an easier way that you could rewrite this to solve? Well, if you think about it, you already know the square root of 16 is 4. So let me rewrite it as the or part at the top. So I can rewrite this as the square root of 16 all raised to the 3rd power. Remember, the square root symbol does not need to be rewritten right here for your index. So that square root index does not need to be rewritten. Okay, so this part I can actually simplify. So instead of putting or, let me put an equal sign because technically it is equal. And I'm going to simplify. So using PEMDAS, order of operations, we're going to take the square root of 16, which is 4. And from there, we're going to raise 4 to the 3rd power. 4 to the 3rd power is going to give you 4 times 4 times 4, which is not 12. It's 64. This is your answer. Whenever you have a negative exponent, you're going to have to do something a little different. If you think back to negative exponents when you were talking about laws of exponents, you can't have a negative exponent. It's not really possible. There's a couple of different ways that you can do this. What I like to do whenever I see a negative exponent, so let me rewrite it so you can see it a little nicer. This is 27, negative 2 over 3 power. I'm going to rewrite this as 1 over 27 raised to the 2/3 power. Well, with this, I can rewrite it in my radical form. So with my rational exponent, I can rewrite it as the cube root of 1 over 27, all raised inside of the parentheses here, to the 2nd power. Okay, well, if you think about it, I could multiply 1 times 1, which is 1 squared, and 27 times 27, which is 27 squared. I honestly don't want to have to do that to simplify. If you look at the 1 and the 27, I can actually take the cube root of those without having to square it to make it work. So I'm going to rewrite this problem as such. The cube root of 1 over 27, and outside of it, we're going to put that squared. Okay, well, if you think about it, from here, we're doing the cube root of 1 over the cube root of 27. It seems tedious to write this out, but it helps you keep track of what you just did. The cube root of 1 is just 1. The cube root of 27 is 3. Now I get to square it. Well, 1 squared is just 1. 3 squared is 9. That's your answer. Go ahead and pause the video right now and try example 3. The great thing about example 3 is it only has a positive exponent. It's rational, so I do have to make a radical, but it's not bad. It's actually kind of nice. So with this problem, with the fractional or rational exponent, I can rewrite this as the square root of 9 over 25. I say the square root because the index of 2 sits right here. The 1 is technically going to be in parentheses around 9 over 25. So technically, if you wanted to, you could put a parentheses around this and raise it to the 1st power, or you could put a parentheses around the entire problem and raise that to the 1st power. No matter what, that 1 is not going to change your answer. So especially when you see a 1, unless your teacher tells you otherwise, I don't usually write that 1 to be 100% honest because it's not necessary. It's not going to change your answer at all. So we're going to take the square root of 9 and the square root of 25. Once we find that, we'll get our answer. The square root of 9 is 3. The square root of 25 is 5. A lot of students will ask me, well, Ms. Tapia, when you take the square root, you're supposed to put the plus or minus symbol at the very front. And usually I'm very happy that they remember that. However, for this question, when you're just simplifying, you don't need to put that plus or minus here. If you look back in all of your notes, the only time we put that plus or minus is when we're square rooting both sides of an equation. These are expressions. Expressions do not need that plus or minus. Only equations do. So let's look at the next page. On this page, it says express the simplest form using positive rational exponents only. Okay, well, let's look at what we have. Ew, this question is disgusting. So the first thing I want to do is try to make it look a little nicer. So the way I'm going to make it look a little nicer is I'm going to rewrite this, especially since it specifically says using positive rational exponents. I'm going to do it this way first. Let me make this disclaimer first. There are plenty of different ways you can solve this. This is just one way that I'm going to show you, just one way. Okay, first thing that I want to do, I'm going to rewrite all of this as a rational exponent, since it specifically says positive rational exponents. That is supposed to be a 2. So this is 27, a to the negative 1 power, b squared, all raised to the 4 over 6 power. Okay, I know I have a negative exponent. There's methods to my madness, guys, so just follow along. From here, I'm going to simplify by trying to reduce this fraction, because just my luck, it actually can reduce. So we're going to make this 27, a to the negative 1 power, b squared, all stays the same, and we're going to raise it to the 2/3 power. Okay, let's simplify it a little bit more. Once you have this, we can distribute that negative 2/3 to each of the exponents on every variable and coefficient. 27 is a coefficient. Since 27 is a coefficient, it's understood, unless it says otherwise, to have an exponent of 1. So I'm going to rewrite my exponent of 1 right here and multiply 27 by 2, negative 1, and positive 1. So 27 raised to the 2/3 power, a raised to the negative 2/3 power, and b raised to the 4/3 power. Okay, from here, I need to see if I can simplify anything. Okay, well, I will tell you this negative, for sure, I think we can all agree on this, cannot stay here. This whole expression is over 1. I need to move this to the denominator for sure. But if I think about it, this 27 to the 2/3 power, I think I can simplify that. Over here to the side, we're going to actually try to do that right now. So 27 to the 2/3 power is the same as the cube root of 27 squared. Okay, well, I don't want to square 27. That's too much work. So we're going to make that cube root of 27 first, then square it. So I'm doing each of these sequentially. Okay, well, the cube root of 27, I could have sworn we just found that. That was 3. And 3 squared is 9. So I can replace this with 9. The b to the 4 over 3 power, especially since it's asking for rational exponents, I can't simplify it. So let me write my answer over here. So we're going to make this 9, like we just found over to the left. I did the work for it. B to the 4 over 3 power over a to the 2 over 3 power. So this ugly mess is my answer. Especially since I asked you to write your answers with positive rational exponents, we're going to leave it like this. For the next 2 questions, next 3 questions actually, it's really important you remember the rules of exponents that you learned back in Algebra 1. So for this question here, we're going to simplify it. If you think back to multiplying radicals, whenever you're multiplying radicals, unless they have the same index and the same radicand, the same index really, you can't multiply it. The radicands, which are the variables and numbers underneath, they could be different. But the index here must be the same, and all of these are completely different. So what I'm going to do instead is I'm going to rewrite these in rational form. So we're going to make this x to the, what is this going to turn into as a fractional exponent or a rational exponent? If you look back on the first page, when you have just the square root of x, you can rewrite it as x to the 1/2 power. So down here, we're going to make this x to the 1/2 power times x to the 1/3 power times x to the 1/6 power. Think back to Algebra 1. When you are multiplying the same base, like we see here, what do you do with the exponents? When you multiply the same base, you add the exponents. So in order to add these fractions, we have to have the same denominator. So for this, to make it a same denominator, I'm going to multiply each of these denominators by, well, technically something different. This will be multiplied by 3. This will be multiplied by 2. And I'll zoom in a bit. The 6 is already fine because I already have that as my denominator. So this first fraction will become 3 over 6. I'm going to add that to 2 over 6, which I'm going to add to 1 over 6. Add it. 3 plus 2 plus 1 is 6. And 6 over 6 is just 1. So x is my answer. You can put x to the first power, but honestly, guys, this is an Algebra 1. X to the first power we already know is without the 1 there. So that's my answer. This guy here. All right, let's look at the next question. With what we just did on the last problem in your head, try to solve example 5. Pause the video and try to solve example 5. With example 5, hopefully you remember you are going to have to distribute. So here and here. So I'm going to rewrite this as the coefficients for both of these terms are going to multiply. The exponents you're going to add. We did the same thing literally right above. When you're multiplying the bases, when the bases are the same, you just add the exponents. The coefficients in front, you just multiply those like normal. So we're going to multiply 3x times x, which is just 3x. We're going to raise it to the negative 1 plus 1, or sorry, let's try this again. Negative 1/3 plus 1/3 power, add those. Negative 1/3 plus 1/3 is just 0. It's nothing. For the next one, I'm going to multiply negative 3x to the 1/3 power, negative 1/3, times negative 4x to the 4/3 power. Okay, well, let's start simple. Negative 4 times 3 is negative 12. X is going to be raised to, we're going to add negative 1/3 and 4/3. When you add both of those, that's going to become 3 over 3, which is the same thing as 1. Anything to the 0 power is 1. So we're going to have 3 times 1 minus 12x to the first power. That 3 times 1 sometimes will affect your answer, but for this question, it doesn't. This is your answer. All right, so pretty easy, right? Let's go ahead and look at example 6. Example 6 is the last question. It looks disgusting, but I'll give you about a 30-second head start. Try to figure out what you can do to start this question off. Let's be honest. There's a couple of things you can do. The first thing you can definitely do is use the rules of exponents or laws of exponents, and since both of the bases here are the same, you could technically subtract both of these, but especially with those radicals anyway, it honestly might be easier just to look at it with a fraction. Keep in mind, there are multiple ways to solve question 6. This is just one way. So for this question, I'm going to rewrite the numerator and denominator with a rational exponent. So we're going to rewrite this as 3x in parentheses raised to the 6 over 2 power, because the index on both of these is a 2. And for the bottom part, for the denominator, the base is still 3x. That radicand underneath is still 3x. And we're going to raise it to the 10 over 2 power. If you look at both of these fractions, they can reduce. I can actually simplify them. So this will turn into, in the numerator, 3x raised to the 3rd power. And for the denominator, 3x raised to the 5th power. From here, think back to Algebra 1 when you were simplifying your exponents. There are several ways to do this. This is how I do it. What I first do is I subtract my exponents. So 3 minus 5 is going to give me 3x to the negative 2 power. Okay, well, once you have that negative 2 power, we just talked about this before. You can't have negative exponents. It has to be positive. So we're going to put this over 1, and I'm literally going to move all of this to my denominator. When I move all of that to my denominator, it's going to become 3x squared, And the numerator, since there was nothing here, since I've moved everything down, you're just going to put a 1 in that numerator. You need to have something there, so put a 1, not a 0. The last thing I'm going to do is simplify it by distributing that squared. So literally doing 3x times 3x, which is 9x squared. Because remember, you're pretty much rewriting this as, and I'm just showing this really quick, you're doing 3x times 3x. 3x times 3x is going to give you 9x squared. This is why I also highly suggest and will take off points if you put a multiplication x instead of the dot. It will mess up your entire answer. However, with that said, this is your final answer.